Deep learning is a form of machine learning that was inspired by the neuronal connections in the brain. In deep learning, there are neural networks with tens to even hundreds of layers of neurons. It's when there's a hierarchy of layers that receive data from previous layers, thus understanding features and representations with deeper and deeper complexity. Deep learning scales to big data very well when you compare it to other traditional machine learning algorithms. However, more data means more training time. If we look here on the right side in this graph, we can see that as the amount of data continues to increase, for performance of the deep learning model, it also continues to increase. However, with older learning algorithms and machine learning, the amount of data actually causes the performance to plateau once it reaches a certain level. Additionally, deep learning models can very easily handle nonlinear problems because of something that they have called activation functions. Deep learning also does not rely on human-created features. Traditionally, in machine learning, features are selected and sometimes created by humans based off of their impact on performance or how much they explain for data set variance. However, in deep learning, there's no need for this because the model actually learns the features on its own. This removes the subjectivity of feature extraction in the pre-processing step. This is something that we call feature learning. If you look here on the right side, we can see this in action. On the top part, we can see that the input is a car, and then a human has to physically extract which features are important for the car before feeding those features into the classification model and producing an output of car or not car. Conversely, on the bottom, we see deep learning. We have a car as an input and immediately feeds into the deep learning neural network, where we can see the feature extraction and classification occurring simultaneously. And this produces an output of either car or not car. So I've heard a lot of people describe deep learning as being a sort of black box where we don't really know what's happening. But that's not really the case. The best way that I like to think about it is that the input layer is just like when your eyes see something. The image that you see gets transmitted through the neurons of the brain so that then it could be understood and you understand what you're looking at. Similarly, in deep learning, the input layer takes in the numerical representation of the image themselves. So it'll take in a pixel matrix representation or voxel matrix representation, and then it propagates those throughout the network. Each node has a weight that then connects to the nodes in the next layer. And each weight also has a numerical value. So some computation occurs, and then an activation function is applied prior to information being propagated onwards. From this, each neuron knows to pass along the information or not, just like in biology where we have the action potential for neurons. It's an all or nothing situation. And so if we look on the bottom left corner where we have the input layer, hidden layer, and output layer, the hidden layer is any layer in a deep learning network that is not the input or output layer. And if we look at the input layer, we have x1 and x2, and out of those we have lines connecting them to the next layer. And those lines have variable names, w1, w2, w3, w4. Those are all the different weights. And so the way that you would compute the hidden layer values is below, where you see h1 equals x1 times w1 plus x2 times w3. And so if you have many more layers and many more nodes per layer, then that h1 would just become x1 times w1 plus x2 times w3 plus etc, etc, etc. You would just keep adding more and more nodes depending on what is going into that hidden layer. So activation functions. These are nonlinear functions whose purpose is to transform and restrict sums to an interval, which helps to determine if information is passed on. So if these values weren't restricted, then as they propagated through the network, the values would actually just keep on getting larger because you keep adding on previous nodes and their weights to other nodes and weights. And as you keep on summing them, this will just continue to balloon and get larger and larger. An example of an activation function is something that we call the softmax activation function. So this takes in 4 or more different values from a layer, and then it transforms, restricts them to an interval between 0 and 1 inclusive, where they become probabilities. The sum of these 4 transform values would sum to 1, and this can be illustrated by the fact that if you have 4 possible outcomes, and each of them has 25% chance of occurring, then if you add them all up together, you have 100% or 1. The network then chooses the transform value with the highest probability and uses this as its output. And this is the reason why the softmax activation function actually comes right at the end of a deep learning network. So here we can see some of the more popular activation functions. On the left side, we have the hyperbolic tangent function, which is also called tanh. And if you look at it, you can see that any input that is -2 or smaller just becomes -1. Anything that is 2 or greater just becomes 1. And then anything between -2 and 2 is sort of linear, very close to being linear. It follows a different distribution. It's not as simple to look at, but beyond that interval, everything basically becomes 1 or -1. And on the right side, we have something called a rectified function, or ReLU. And in this function, anything that's 0 or smaller just becomes 0, and anything that's greater than 0 is just itself. So it's linear when it's greater than 0. And ReLU is actually by far the most popular right now, and there are a lot of different variations of the same activation function. So just to wrap up how deep learning works, each model then has a cost function that's supplied by the user. The cost function evaluates the error by getting the difference of the actual value and the predicted value. Naturally, we want to minimize the error. In particular, if we think of it as the actual value is 1 and the predicted value is 0.7, that means that the error is going to be 0.3. So the closer that we get it to be 0, that means the closer that the actual value and the predicted value are together. Based off of the error, the weights then are changed by propagating backwards to minimize the cost function. This is something that we call back propagation. So the way that this best weights are found is by using something that we call the stochastic gradient descent algorithm, which rapidly finds the optimal weights to minimize the cost function. So effectively what's happening is that we've reached the end of the deep learning algorithm, and now we're computing what the error is and the cost function. And from there, we know the algorithm knows that it wants to make the error as small as possible. And so it'll go back into the network and actually change what the weights are in order to try to make the error smaller. Conversely, the forward process, which we discussed earlier, is something called forward propagation. So to put together what we've talked about so far, first, we initialize weights randomly as values close to 0. Then, you input your first observation into the input layer. We go through forward propagation, so the neurons are activated, each activation is limited by the weights and the activation function. This propagation goes until the output layer. Now we evaluate the error. Then backpropagation occurs. So we backpropagate the error. Weights get updated based off of how much they impact that error. The user actually inputs the learning rate, which is a part of the stochastic gradient descent optimization, and that determines how much we update the weights. When the whole training has passed, that is called one epoch. Then you would need to repeat with more epochs. So a learning rate that's lower means that the model actually learns more slowly, but that also means that it's going to be more exact with finding an optimal solution, because essentially each time that it's adjusting, it's making smaller and smaller adjustments so that it'll get more and more close to the optimal solution. However, the issue is that this requires more epochs, which means that you have to increase the amount of time needed for training a model. So, then the question becomes, well, what do we use in imaging? Typically, the best machine learning model considered for imaging nowadays is called the convolutional neural network, which is a type of deep learning network. These models are particularly good with grid-like inputs like a pixel or voxel matrix, and that's exactly what we want for imaging. So, to explain how it works, a convolutional neural network essentially takes an image matrix, computes something that we call dot products, and it does that repeatedly. These dot products are between the data and a matrix called a kernel. The output of this is a new, smaller matrix. This is called convolution. You can see this illustrated on the graphic on the right, where we're taking smaller pieces of the matrix, doing a computation, and then producing a new, smaller matrix. After we're doing a convolution, just like in trivial deep learning, which is what we talked about before, we apply an activation function. Then we do something new called pooling, and we're going to talk about what that is shortly. Finally, there's a fully connected layer at the end, which we'll talk about in a bit as well. So pooling layers. These can sometimes replace the standard output of certain layers. They output summary statistics of the output from a layer, which decreases the number of computations and weights. So summary statistic can be maximum, minimum, mean, median, mode, etc. A popular pooling layer is something called the max pooling layer, which will output the max values in different areas of the matrix depending on the filter size of the pooling layer. So if you look here in the graphic, we can see that the pooling size is 2, and so we take each 2 by 2 matrix that's side by side, and then we find the max in it. So in the top left matrix, we have 6. The top right matrix, we have 8. The bottom left matrix, we have 3. And in the bottom right matrix, we have 4. So then on the right side, where there's a new matrix, it's just those maximum values. So why even bother using a convolutional neural network? What makes it any better than a normal trivial deep learning network? Well, unlike in trivial deep learning, which computes interactions between each individual input and output neuron, the convolutional neural network, because of its use of a kernel that's smaller than the input and doing all that computation with the dot products, means that we end up gleaning important information from hundreds or even thousands of pixels at a time, instead of from each individual pixel. This ends up lowering the number of parameters, which increases statistical efficiency and decreases computation time. This is called sparse interaction. Additionally, the decrease of the number of parameters means that we don't run as big of a risk of doing overfitting, which is when you can't generalize your model to other use cases. Another reason to use convolutional neural networks is because, well, let's think about it. It's fair to assume that computing a feature at one point could probably have important information at another point. If you find grass in one part of a picture, chances are when the model finds something that looks like grass in the other part of the picture, it's probably grass again. In a trivial deep learning model, we would only use the weights one time, but a convolutional neural network shares parameters, so the weights that are applied in one place can actually be applied elsewhere. Finally, this parameter sharing means that convolutional neural networks have something called equivariance of translation. This is when you change the input in some way would actually cause the same change in the output. So if you double the input values, you double the output values. So to wrap up convolutional neural networks, we have a diagram of one right here. So you have the input layer. It gets put into the model. And so you can see in the middle that we have all these different hidden layers. So you have a convolution with the activation function ReLU that shrinks everything down a bit. Then we have pooling layer, which takes the summary statistics from the previous layer. Then we do another convolution, and we apply the activation function again. Then we pool again, and then we do something called flattening, and that produces the fully connected layer. And what a fully connected layer is something that essentially takes the high-level feature representations and then checks what classes they correlate with. So if we imagine that the final classes that we have are cat, dog, pig, horse, etc. Different sorts of animals. Then high-level representations in the fully connected layer may be forelegs and paws for a dog or a cat. And so the fully connected layer just has these very big, overarching ideas that correlate well with certain classes for the output. Дякую.